Wait, open it in Firefox. Open it in Firefox. What? I'm going to start the recording because we're so far into this, but open it in Firefox. Yeah, open it in Firefox. You need to see it Firefox.
It should be on there.
Well, I see that the HTML file is associated with Firefox. Although I don't think I would open that HTML.
Firefox? That's pretty dangerous. Oh, sorry about all that.
All right, thank you everyone very much for waiting with us. The second Windows PC set work. So we're all good now. Thanks everyone.
Make sure you stand by the microphone so you get audio on the video, or at least face the microphone.
Can everybody hear me? Yeah? Of course. All right, so I hope everybody can still hear me. Usually I talk really fast, I have to slow myself down, but today I'm going to lean into it because I'm really far behind. I have a lot of stuff to go over, so lucky for us, it still works out. There's silver lining. I was hoping only I could see that. All right, so this is the agenda. So we're going to real quick go over kernel exploitation basics. We're going to cover some of the common vulnerability classes, so the types of things that we see. And then we're going to dive into what those classes mean to us when it comes to things like reliability, the types of tricks that we can use. How do we take that vulnerability and take that and use it to get code execution, which that's what we're always after, right? So yeah, we're gonna talk about executing code, and then we're gonna hit on mitigation technologies. So we're gonna talk a little bit about SMap and things like that, and some of the newer technologies, and some of the problems that we have that are running into these. We're going to talk about kernel exploits in Metasploit framework, so how they're actually implemented. We're going to talk about the basic two different types of kernel exploits as they're implemented for the Metasploit framework, and then some of the common techniques that they use, which is very, very interesting, at least from my perspective, because a lot of the Metasploit exploits are some of the more reliable kernel exploits, in my opinion. So what are the techniques that they are using? How can they be applied to other exploits, standalone ones, if you are so inclined to not write it for Metasploit? And then finally, we're going to talk about improving reliability, because really the reason why I wanted to give this talk is that there's a ton of really awesome kernel research, kernel exploit research out there, and it's really good, but I find a lot of it is not particularly practical. They're always talking about these edge cases that, if the stars align quite right, you can get to this amazing type of vulnerability, but a lot of times they're not always the most reliable exploit, and a practical exploit needs to be reliable. A lot of you in here are probably pen testers. Can I see a show of hand real quick of pen testers? Okay, so on the flip side, if you consider yourself to be a vulnerability researcher, can I see your hands? Okay, so not quite as many vulnerability researchers. I hope everybody gets a little bit of something in here, but a lot of you are pen testers, and what's probably the most important thing to you is these reliable. The exploits need to be reliable. That's going to be the first and foremost thing, because if your exploit is not reliable, you're going to lose that shell, and nobody wants that. It's never a good thing. So just a little bit about me. My name is Spencer. I work at SecureState, do R&D. I introduce BSODs. We're going to cut that short. A lot of the things in this presentation will cause blue screens of death. There is, just like in other problems, there is no one solution that fits everything. So what we're going to try to do is we're going to try to minimize the blue screens, and we're going to talk about the different techniques that we can use to do that. So that's a blue screen right there that I was running into with MS-1440, working on that a little bit last year. So some of the basics. So why kernel exploitation? Why do we care? There's been a downward trend of remote code execution vulnerabilities. Arguably, one of the last great ones was MS-08067, all the pen testers' favorite, that reliable code execution that you can still find. I found it on a domain controller. It's kind of sad, but it is starting to become less and less apparent because people are actually patching them. So RCE is now generally being found in third-party libraries and things like that. So we are getting things, we are still seeing RCE, but they're not quite as prevalent in the Windows source. So one of the reasons why we want to have kernel exploits is that the kernel is always there. The Windows kernel is always going to be there. So it's an attack surface that is not easy to get away from. Unless you're running Linux, you're probably going to have the Windows kernel. There's not really any way to mitigate that. Also kind of leads us into why you see a lot of client-side exploits that leverage kernel vulnerabilities as a sort of second phase to once an attacker compromises like a browser or something like that. They leverage a kernel vulnerability to escalate themselves, and they can usually get out of some type of sandbox or things like that. A lot of these ones we're seeing are being released from like Pwn to Own. There's a lot of like fantastic bugs that are coming out there, and then after the researchers release them there, they have their day. They're usually released in like write-ups afterwards, so like people can actually figure out like what they did, and they disclose the vulnerabilities that way. So we're seeing a lot of great research coming out of the Pwn to Own competition as far as kernel bugs. Another fantastic resource that we're seeing a lot is the Google security research team. They're releasing a lot of kernel vulnerabilities as well. So kind of to look back on it, these are a bunch of the kernel bugs that I found to be notable. The reason why I found these ones to be notable is that other than the typical Microsoft boilerplate, something was wrong in the kernel verbiage, there was some type of additional either research or some type of code to go along with it. Somebody actually looked into taking this bug and making it into a actual full-blown exploit, into leveraging it. So there's quite a few of them. There, the latest, this MS-15097, was actually released onto ExploitDB as a proof of concept now service. That was actually earlier this week. So there's a lot of really great stuff there. So we're talking about common vulnerability classes. So I have them here broken out. The top three are the primary ones. So we're going to talk about write, what, where, null pointer to reference, and then use after free. And then finally, we're going to have an honorable mention for stack buffer overflow, because usually when people think about vulnerabilities, they talk about stack buffer overflows, but they're just not quite as prevalent in like kernel land. I can't really think of any like recent exploit for like a Microsoft driver that leveraged a stack buffer overflow. Not to say they don't exist, but once again, we're really going to be focusing on the common vulnerability classes. So while they are common in other types of software, code execution, things like that, not always in the kernel land specifically. So first up, with write, what, where. So what is it? It is sometimes attacker-controlled data can be written to an attacker-controlled location. Now this is fantastic because an attacker can usually leverage this by writing data that to a location that they control. Now it's usually more important for the attacker to be able to control the location of the data more than what the data actually is. Of course, if they have full control over both of them, usually getting code execution is trivial from that point, because there are a lot of really well documented techniques of what the Windows structures you can corrupt are that will give you access to code execution if you control both the what and the where, as long as you know where it is to go. So exploitation using this is often relatively stable. The reason why is because usually when you have a write, what, where condition, people end up attacking, they end up targeting the how dispatch table. So there's a special pointer in the how dispatch table at the offset of 4 on a 32-bit system that is a callback. So if you can target that as your where and you have your what data, you can trigger the code that is written at that, or that is pointed to by that pointer that you can overwrite to be executed on demand. And being that it can be done on demand is very key to us for reliability, because what we can do is we can exploit it multiple times to, for example, elevate ourselves and then clean up the system after we're done, things like that. In addition to that, usually corrupting that table, it generally doesn't lead to, it's less likely to lead to instability, because the system calls that trigger that the pointer to be called are not quite used as frequently as some others. So some of the common exploits that utilize this technique is MS-1180 was a AFD join leaf write, what, where condition that was released by OffSec back in 2011, and then more recently CoreLogic released MS-1470, which was a bug that affected Windows Server 2003. Much more recent. That was released like 4th quarter of last year. So next up we have null pointer to reference. So this occurs when like a null pointer is referred to as an object. So of course why this is bad is that if an attacker can map the memory at that address, then they will actually be able to create potentially a malicious object at that address that can be used. And depending on what that object is going to depend on how it is actually being used. So it's going to lead the attacker to need to know what types of objects they could put there and how it's being referred to. So exploitation can be a little bit more complicated because they're going to have an understanding of what the structures are, how they can be used, and how the vulnerability is treating them when it is triggered. So Sometimes the null page cannot always be mapped. There's a mitigation for that, null page mapping. Emmet it includes that, and I believe on Windows 64-bit systems by default, like it's just always on. You can't allocate the lower pages. You can't allocate that null page in memory, which is a little bit of a problem. One thing that is interesting about this, though, is that sometimes as was seen in MS 1458, is that a pointer can be truncated. So whereas on a 32-bit system, -1 was actually being used, on a 64-bit system, it was this like 000 FF. And what's very interesting to us about that is that instead of the null page being referred to as an object, this address that is much higher in user controlled memory space was being used. And so because of that, an exploit for 64-bit was able to be written because that is outside the boundaries of where Windows has their protection in place. So they're able to leverage that. And so there's a reliable 64-bit code execution for that because the pointer was truncated. All right, so use after free. So use after free is kind of similar in the sense of null pointer to reference, in that a invalid memory location is being used to refer to an object. So this is, out of the three vulnerability classes that we're talking about, this is probably the one that is most difficult to reliably exploit, because usually it requires you to successfully reallocate the memory that was originally free. And that's very critical, and it's not always an easy thing to do. Much additionally more difficult about that is you don't always know, and you can't tell if you have successfully reallocated that. We'll get to that a little bit more in a later point in time. But one of the examples of this vulnerability was MS 1510, which was a scroll bar info use after free. All right, so how do we take these vulnerabilities and actually get code execution out of them? Because a lot of times, if you trigger the vulnerability, you get a blue screen. That's fantastic. You're able to trigger that vulnerability, but we don't want that. Once again, like I said, as pen testers, you want the exploit to be reliable. You want it to work first time every time, so you're not going to lose your shell. That's the most important thing. So you need to be able to do that very carefully. So like I said, with the write what where condition, pretty much the go-to technique is to be corrupting the how dispatch table, because there's that pointer at that offset. It's on all the versions of Windows, like XP all the way up to Windows 10. And you can actually resolve that symbol. That's another very nice thing about it, is that with the NT, Kah and LPA, you can resolve the symbol out of that, and so you can calculate the offset to where that is in memory. I say that, however, you should note that in order to do that, the exploit needs to be of the native architecture of the operating system you're attacking. And what I mean by that is that if you are running in a WoW64 process, it's going to be a lot more difficult because you can't load that executable in to then call load library A on a get proc address. So it works a lot better if you're in a 32-bit or a 64-bit process. In terms of Metasploit, however, that just usually means that your interpreter session needs to be the native architecture of the system in order to be able to resolve that address, which is why you don't usually see a whole lot of WoW64 exploits. It just complicates things a lot greatly. Pwn to own, though, a lot of times they are forced to do that. So if you want to look at them, then some of the pwn to own research that comes out of there is fantastic. NT query interval profile is that function that I mentioned. So once the how dispatch table is corrupted, because you control what data is written and where it is written to, you set that where to be this offset in the NT how dispatch table. After you have done that, you have that the what condition, the what you wrote to that should point to your shellcode that's going to do whatever it is that you would like for it to do. After you have that, you then can call NT query interval profile to trigger your shellcode on demand, which is very flexible from an attacker's perspective, because if you have control over where the shellcode is, you could potentially change the shellcode because it's in your process memory space without retriggering the vulnerability, to then call NT query interval profile again to execute different shellcode in the context of the kernel without retriggering the exploit, so without having to trigger the write what where condition again. And the fewer times you can trigger the exploit condition is of course going to increase your chances of stability. So if you don't have to do any more of that is necessary. So no pointer to reference and use after free. They're similar in the sense that they are object dependent. Like I said, it's going to require the attacker to know what the object is and how it's being used as in order to be able to get some type of a structure corrupted in such a way that's going to be useful to them. I end up reading a lot of write-ups on these use after free vulnerabilities and null pointer references. I'm convinced there's some secretive like reference that everyone has that like points to like the different locations and like what types of structures can be used and how. There's not really good reference to my knowledge on that. It's kind of up to the attacker to figure out how that structure is being used and then to look up the usually non-existent documentation on it. Usually they have to end up reversing a lot of how the code is being referred to in order to find a way to leverage it. So the object ends up getting, it ends up getting corrupted. Either you're corrupting it or you're providing your own object, and it is sometimes corrupt because you don't always have the ability to create a fully legitimate one. In a use after free, the object is that is freed, you end up having to replace it. It's not always with the same type of object, but it does have to be the same memory location, which definitely impacts stability, is that you need to be able to reallocate the region that had been freed. And there's a lot of different factors that go into that, such as the different types of heaps. Newer Windows have added in additional types of heaps, and so objects are always going to be created on the same type of heap, but not all objects are used in the same destination heap. So you need to be able to target and know what objects are used in the same heap that you're targeting, so that those objects would be applicable, that you might be able to initialize over the area that had been freed. So usually when trying to look for an object to replace the one that had been freed, you're looking for some kind of a primitive. Usually the primitive ends up being ideally something that can be used to once again achieve like a write but where condition. You're looking for some type of a pointer that you can call a function on this object that allows you to write data to a location that you control. So it's usually trying to go for primitives either like write conditions would be ideal, would be the most ideal. Second, of course, to call, but that's not quite as frequent. But read conditions are also beneficial because you can leak out additional data when that happens. So one object that I did want to point out that is a fantastic object that if you can corrupt it is relatively easy to achieve code execution with, and that is the tag WND object. So that is the window object that's stored in kernel memory space. And so it has all of the information that's pertaining to the window that you're of course using in the GUI. And so what's very useful about this object is that it has two fields in the structure. The B server-side window proc is a bit flag that's normally set to 0. But if that flag can be set to 1, then this LPFN WND proc, the pointer points to a callback. And when that server-side window proc flag is set, when you send events to the window, that WND proc function will be called in the context of the kernel. So if you can set that flag, you usually already have relatively easy access to the window proc function because there's Windows API functions to call it, or excuse me, to set it. But usually because it is set to an address in userland, Windows makes it easy to set that. But that server-side window proc flag is what's always 0 and is what is really protecting the system usually from that vulnerability. So if you can set that flag, you can then send an event to the window, and once again, you can usually achieve code execution on demand in a relatively reliable way. All right, so mitigation technologies. Unfortunately, the days of jump ESP died with XP. Those are long gone, and it's just not realistic to think that you're going to find vulnerabilities and be able to exploit them with like jump ESP anymore. ASLR is only a semi-issue because usually when you are running a local privilege escalation, when you are running an attack against the kernel, you already have code execution usually. In terms of Metasploit, this usually means that you're loading a DLL or you have an interpreter session and you can like make Ruby API calls using Railgun. But you can usually use those to resolve addresses at least out of user land. So you can have that ability. And once again, like I was talking about the NT-HAL dispatch table, you can actually load the kernel executable into memory so you can resolve the address of that NT-HAL dispatch table. So ASLR is an issue, but it's only kind of an issue, so it depends on what exactly you're trying to corrupt and where it is. It's not as much of an issue as it is for like remote code execution where it's purely a black box. You have usually no idea where the addresses are unless you have some kind of a leak. So some of the kernel addresses are also still usually at static offsets. Sometimes some of the tables are always at like static offsets. So if you need to use those, those are available as well. But for the most part, the kernel modules are randomized, but once again, you can still usually resolve the addresses, the base addresses of the Windows kernels. And then data execution prevention. So once again, because you have code execution ahead of time, execution prevention is not usually a problem because you can set the permissions on the page. Now, that did change with the introduction of SMap in Windows 8, but we'll talk about that in just a second. So additionally, there's null page mapping. That is one of the protections provided by Emmet. I believe you can also enable it in the within the operating system without using Emmet. And like I said about 64-bit Windows, that 64-bit Windows has that baked right in. You cannot allocate those really low-level, those low-numbered pages on a 64-bit Windows from a user process. It just doesn't allow you to do that. What they end up actually doing to mitigate that is that the operating system maps that page ahead of time and sets the permissions to like no access. So it's basically the operating system's just going to squat on that page so that the process cannot allocate it to use. And then so there's SMap. SMap was originally designed by Intel and introduced into their processors long before Windows 8 came out, but it wasn't until Windows 8 came out that the operating system did start to take advantage of this feature. Now, what SMap does is SMap prevents userland addresses from being executed within the context of the kernel, which can definitely be a problem for an attacker because usually their shellcode is in a userland address space. If they're trying to get around like def or something like that, they probably allocated a page with read, write, execute permissions, wrote their shellcode to there, and then had some type of a primitive in order to get that to be executed. But because that is in userland, SMap is going to prevent that from being executed. It's going to throw an SMap exception, which looks just like that on Windows 8.1. So that attempted execute of no execute memory. So in the SMap PSODs. So there's actually a fantastic technique that can be used to disable SMap. It is in my references. What they ended up doing was they ended up finding ROP gadgets in the Windows kernel that if those gadgets could be executed, they could disable SMap. So what you end up doing in order to disable SMap is you end up resolving these addresses out of the kernel and then executing those, and then when that returns, you have to have some type of a technique in order for it to then be executing into your shellcode. And so there's fantastic research on that, and there's a great white paper on it. One of the more difficult things about this, though, is that unlike the NT-HOW dispatch table, the address of these ROP gadgets cannot be directly resolved because it's like buried down within a function in like the page LK section. But what you can end up doing is you can still do something similar by loading the kernel executable into your process space. You can search that page LK section by processing the PE headers, and then you can search for the ROP gadgets, and you can use that to be able to determine the address of the gadget suitable for disabling SMap. And what that's going to do is that gadgets can disable SMap by setting the CR a flag in the CR4 register, and then after that's been disabled, you can execute your code in a userland address from the context of the kernel. So once again, the kernel can't be loaded in on a 64-bit system. The kernel can't be loaded from a 32-bit process because it is a 64-bit executable. So I suppose you could like write your own parser to do that, but it is a little bit more difficult to do that because you can't use the raw Windows API calls to just load it and then process it from there. So next up, we're going to talk about how they are in Metasploit, now that we have a solid understanding of the different vulnerability classes and how they can be used, leveraged to gain code execution. So pretty much all the kernel exploits in Metasploit are all the local privilege escalations that you find under Windows, exploit Windows local. So they're divided into two different categories based on their implementation. They have exploits that are implemented entirely in Ruby, and they have exploits that are implemented in C as reflectively loadable DLLs. And so there's advantages to both of these approaches. So they don't have to necessarily be local privilege escalations to be a kernel vulnerability, but most of the ones in Metasploit and certainly under that category are. There are a couple of Windows kernel exploits, but they're outside of that specific tree, and so what we're focusing on is we're focusing on those privilege escalation vulnerabilities that are these two classes. So most of them are going to try to directly either steal the token or duplicate the system token. Now, each process has a token reference in it, which is what identifies the process as being controlled by a specific user. And so the object of local privilege escalation or kernel vulnerability is going to usually be to swap that token out for a system level token, which can allow the attacker to do things, of course, with system level privileges, because the system is going to think that that's a system process because you swapped out the token. There's one exploit in Metasploit that does not attempt to modify the token, and that's the MS1353 exploit. This was one of the ones that came out of the Pwn to Own competition, and that one takes an approach different. It doesn't directly try to either copy or duplicate the system token, but what it actually does is it clears out the ACL of a system process. I believe it's when login, and once the ACL is cleared out, is that the process is able to inject a payload into the when login process. That way you can utilize that. So that's a different technique, but that's the only exploit that uses that. Most of the other ones are all going to try to either copy or duplicate or create a new token. There is a Windows kernel exploit mixin for some convenience methods. So these methods exist to be able to like resolve the address, the NT-how dispatch table. There's token stealing shellcode in there, and things like that. So Ruby implementation. So why would you want to write a local kernel exploit in Ruby? First off, this might eventually be deprecated in favor of the reflective DLL steps because there's a lot more advantages to that. So currently, there's not really a whole lot that are being done in this realm, but a lot of the older local exploits are implemented entirely as Ruby files using like Railgun. So this technique is well suited for exploits that are very simple, that generally trigger some type of a write while where condition, which is common with like the NT device IO control file centric exploits, of which like MS1180 that I mentioned, the AFD join leaf one is one of them. So you can utilize the NT device IO control function with like a specially crafted buffer, and that's what's necessary to exploit MS1180, is that that specially crafted buffer allows you to control what data is written to where. And so one of the benefits, I mean, it's an entirely self-contained Ruby file. I know a lot of people shy away from writing in C. A lot of people, if like you're a pen tester, you're just trying to get into it, you may not want to write an exploit in C. That's a lot more code, and I think if you're looking at it, it might be a little bit more intimidating. But if you're writing it in Ruby, like this technique can be very useful or well suited for ones that are relatively simple, that just make that one call to sort of trigger like a write while where condition. Now, the C implementations, they're a lot more flexible. They allow faster, easier access to the Windows API. And so one of the other nicer things about this is that because the exploit is implemented as a DLL, Metasploit can actually load that either into its own process or it can elevate another process for you, which is something you can't do with the Ruby implemented ones. Now, why would you want to escalate another process is because if something goes wrong and that process becomes unstable and crashes, you're going to lose your session. So the reason why you'd want to escalate another process is that if it fails and it doesn't blue screen, you'll still have your session. And that's a big if. That requires that you still that it's not going to fail in kernel land, it's not going to blue screen. But if it fails in user land, you'll at least still have a session. A lot of the exploits are implemented this way, so what they'll try to do by default is they'll try to spawn a new process, inject its payload into that, and then inject the DLL to elevate the other process, like Notepad or Calc. Sometimes sandboxes prevent this, though. If you ran into like a browser exploit and you can't actually start those other processes, Meterpreter will fail back to loading the DLL into its own process to elevate that one instead, so that way you can still try it as a sort of last-ditch effort. But once again, if it fails, you're going to lose your session, whether it be SODs or not. Okay, so most of the exploits take like a basic like 4 steps. They do some type of like an environment detection to check to see if Meterpreter is already running a system, and if it is, you want to bail out because there's no point in continuing, and if you trigger the exploit again, there's always that chance of instability. So you don't want to do any more than is necessary. A lot of the Windows local kernel exploits in Metasploit also, they do a check method. They have a check method that's going to try to see if the system is vulnerable. And the way most of them do it is they end up loading, or they end up looking at the driver on disk, and they end up checking the file version of that against the patch version to check to see if that version is patched. This would also be the phase where they would want to do any type of detection against like the version of Windows, make sure you're running as the native architecture, not in like a WoW64 process. A lot of times they also run the check method and they won't let the exploit continue if it doesn't look like the system is vulnerable, because there's a good chance, once again, that you're going to cause system instability and you're going to lose your shell. In addition to BSODing the box, most likely. And so once again, so the ideal process is that you want to start up a dummy process of like Notepad or something, and you want to inject and elevate that one so that if there's some type of a failure in user land, you're not going to lose your session. And then hopefully that DLL will do its job and elevate you to a system level process. Okay, so shellcode time. So optionally, shellcode can be either implemented as like raw bytes is what we usually see, but we've kind of also started to see a shift in some of the newer exploits to using C-based shellcode, which once again is not something you can do with the Ruby exploits, but in the reflective DLL ones, you can write a function and have that be executed as your shellcode. So one of the advantages to that is that the shellcode can be a little bit more flexible. When you are dealing with the raw bytecode and you have like an assembly stub that's going to steal your token, that's going to be dependent upon the version of Windows that you're running, because the different versions of Windows are going to store the token in a different part of the structure. So it's going to be a different offset. So the shellcode has to be specific to your version of Windows, which once again, that can be a source of instability. So if you can use shellcode that's implemented in C, a couple of the latest exploits in Metasploit have used ones that actually search for and copy over the shellcode, and then that implementation, because it's searching for, it's a lot more dynamic, and it's not going to be specific to a single version of Windows. In addition, the code can be executed on both 32-bit systems and 64-bit systems, which is also something that you can't really do with just like the raw byte code, which used to be really popular. Okay, so once again, we talk about reliability because nobody wants a BSOD. Okay, so sources of instability, what's going to cause things to be unstable? It's going to be corrupted structures in terms of things like use after free. That's probably going to be the #1 most common source of instability, is that you're going to corrupt some kind of like a system structure, whether it be like something on the heap or some other type of object, a window, some type of like a linked list. The possibilities are endless. There's a lot of things that could be corrupted. Another source ends up being token reference counting. So each one of those tokens that are identifying the process and who owns it has a reference count. So if you sit there and you run an exploit multiple times and it's blindly copying over this system token, what happens is that when that elevated process exits, that system token, the reference count on it is decremented. And because the shellcode most likely did not increase the reference count, once the reference count reaches 0, that token object is going to be freed, and that's going to cause instability when there's references to that missing object. So you don't want to do that, because you can cause instability. And then returning control after elevation. So after your shellcode executes, how do you get control back to the attacker so that they can continue what they're doing? They need to be able to launch an interpreter session or elevate themselves somehow. They need to actually do something with the process that they were able to elevate. So corrupted structures. One of the nice things about Windows is that there are certain objects that are in a shared region of memory between the user land and the kernel address space. So there's a region of memory that's read-only to the user land, but you can actually look through this, and only the kernel can write to it, but it's included as read-only to as performance increase, because every time something is done in the context of the kernel, the context has to be switched, and that can be very slow. So in order to speed this up, Windows makes some of the structures in a specific region of memory available from the userland process so that those can be read. So if one of the objects that you're messing with is within this region, what you can actually do is you can look through this region to see if perhaps you've been able to corrupt it successfully, or if you've been able to like reallocate it. You can kind of look at that and see if you think that continuing the exploitation process is going to cause instability or not. And ideally, if you see that there is something wrong, that you weren't able to corrupt a structure in just the right way, you can bail out of the exploit process prior to triggering some type of an instability. So this shared region, it exists in versions prior to Windows 7. However, Windows 7, there's a pointer to it that is in user32 DLL that actually tells you exactly where that region is, so that way you know where that is, and so you can look through that. Some of the objects that are stored on there is going to be like the handle table and like the Windows objects, so like those tag WNDs that we were talking about are all going to be stored on there, and they're not usually used by like user processes, but they are available from the user land. One of the things that you can do if you are backing up structures on this page that you can read is you can back it up. Prior to starting your exploitation process, you can take those structures that you might end up corrupting and copy them over to another region of memory. And if you can copy them back prior to anything happening, that's maybe like the last step of your shellcode. The last step of your shellcode, you copy that data back. You can usually avoid system instability from that perspective. Not always the case, though, because once again, that requires you to be able to read it from the user land before getting the exploit started up. Yeah, and then once again, like if structures are going to be corrupted and code execution doesn't occur, then usually the system is going to die, almost always, because if you don't have that ring 0 execution, it's very difficult to be able to clean up after yourself. It's going to very much depend on what types of things are being corrupted in the access, but most of the time, the system is going to die. So token reference count. So this usually becomes a problem when like exploit is stealing the token and it's executed multiple times. So they have that reference count. So the different types of things we can do to avoid that is we can use that that ACL technique that was used by MS-1353, where you actually clear out the ACL of a process and inject into that, because then you're not messing with the token, so you're not adjusting the reference count. However, if you're, as you probably know, as a pen tester, you don't usually want to inject into an already running system process. That can also cause system instability. There's a lot of processes that if you inject into that, something goes wrong and that process dies, Windows is probably going to shut down. So not always a good thing. So duplicating the actual token and duplicating it intelligently, so you can usually I believe there's a function in the kernel that you can call to actually duplicate a token. So that's going to safely copy that token over into the new process, so that when the elevated process exits, that reference count is not going to be corrupted. You can back up the original token, do what you need to do, and then restore it. Now, this is very useful when if you have like a write while where condition, and once again, like you can trigger your code execution on demand in the context of the kernel. You can have two sets of shellcode. You can have one that's going to blindly steal the token, and after that executes, it gives control back to the attacker. They can then do what you need to do because you're running as a system process. You can spawn a new interpreter. You can do whatever it is, but before that process dies, you swap out that shellcode with shellcode that's going to put the original token back. And if you put that original token back, then your process can exit out cleanly, and it's going to be that original token's reference count that gets decremented. So you can put it back if that's an option as well. That's going to require that the exploit needs to be triggered twice. So that's not always a good case depending on the class, but if it is that like write while where condition, you corrupted the NT how dispatch table, this is a viable vector. So returning control. So what do you do after the process, after elevation? So how do you get control back to the attacker? Because once again, you elevated for a reason. You want to actually be able to do something with it. So you need to be able to find a location that you can actually return control to. You need to be able to return execution back to it. So one of the things you can actually do is you can unwind the stack in assembly. Microsoft uses a standardized calling convention. So what that means is that every time a function is executed and returns, the calling convention is what dictates how the registers are set up. And so because it's a standardized calling convention, almost all of the Microsoft code is going to utilize this one convention. Which means that you can actually like unwind the stack, and what that means is you can determine how many frames up the different functions are of how like deep you are. It's like how debuggers are going to be able to work. So using this, because it's relatively trivial to be able to determine if an address is a user land address or a kernel land address, you basically can tell by looking at the numbers. What you can do is you can unwind the stack and you can look at the call stack and see what function is the last function before the kernel switched context into kernel land and which one's the last one before it goes back. So what you can do is you can actually return to NTKI system service post call, which is one of the last addresses in kernel land, and what that's going to do is it's going to switch the context back, and it's very critical that you switch the context back, because once again, if you just hop back into userland directly, the kernel is going to be in an inconsistent state, and you're probably going to cause a lot of problems. But if returning directly from your shellcode is causing issues because the function is using an object that you have corrupted somehow or something like that, which is very common, you need a way to be able to return execution after executing your shellcode in order to be able to continue. So the KI system service post call is the address that is executed in order to switch the context back. So set everything back up so that way the user can, the userland code can continue executing. And the userland code is where the attacker is and has full control, so that's when they can do whatever malicious things that they need after that. Using this technique, you can also manipulate the registers in order to be able to set up whatever return value you want to have for that system call. Most of the time, people would probably, their first instinct would be to have it return success. But that may not necessarily be the best idea, because if you're calling userland code, if it thinks that the system call completed successfully, it's probably going to try to continue. It doesn't know any better. If you told it it works, it's going to think it works and it's going to continue. And if it continues, it once again might trigger something that everything is in an unstable state that might cause like a BSOD on like another system call. So what you actually might want to look at doing as an option is play around with the different errors that you can actually return. Because if you return an error, the code is probably going to return control directly back to the attacker without continuing on and using those corrupted structures. So probably can't see that, but this is 32-bit shellcode that demonstrates that. So it just basically unwinds the stack and it compares the addresses of each one. So it counts up how many frames deep it is, and then it calculates or counts up how many frames deep the kernel addresses are. So that way you can jump back into the last frame before, which is that NTKI system service post call. Yeah, so it can return back into that and then switch context back into userland to continue. So 64-bit exploitation, it's starting to pick up. There's actually the latest Windows local privilege escalation that was added into Metasploit was just targeting Windows 8.1, and I believe that was a 64-bit exploit. So it is starting to pick up. One of the really nice things is that 64-bit uses one calling convention, which is very nice. 32-bit Windows, they had like standard call and SDECL and fast call and this call. But for the most part, on 64-bit systems, everything's going to be just the one calling convention, which is nice. Like I mentioned, WoW64 complicates a lot of things, specifically resolving of addresses, because a lot of those addresses that are in like that kernel executable is a 64-bit executable, and you can't load that into a 32-bit process, so you need to have different ways in order to be able to resolve those addresses out. And then so if you are looking at a vulnerability on a 32-bit system and for whatever reason it doesn't work out, or even if it does, if you want to look at it on a 64-bit system, check for pointer truncation to see if the pointer is actually, if the value is different, if that might mean different things for you. In the case that I did for like MS-1458. So closing thoughts, kernel exploitation is really flexible. It's because the attacker has code execution ahead of time. They can set things up. They have a lot more pieces to the puzzle. They can sort of play with things. They can massage the system into such a way that it benefits them and that the attack is more likely to succeed. Also, like mid-attack, they can sometimes be able to like check if the structures are corrupted, bail out, and things like that. So it's a lot more flexible than it is for like a remote code execution typically when the system is a complete black box and the attacker has no way to know anything on there. Additionally, size doesn't matter for a local privilege escalation. A lot of the exploits in Windows are like full-blown DLL, so you don't really have to worry about like size restrictions like you do in a remote code execution vulnerability. Your shellcode will fit because you have an entire DLL loaded into memory, so that's not a problem at all, which is very nice. My own personal hypothesis, kernel exploitation is definitely going to stick around. It's one of those vectors just because we're seeing a growing trend of like client-side attacks, whether it be like browser exploits or Java or Flash 0 days or phishing. Phishing is definitely one of the biggest, is that we're seeing a lot of pen testers are most likely using things like McIntyre and Metasploit and things like that to get compromised systems by phishing, and when they do that, usually, hopefully, they don't already have system administrator access. So this might be one of the techniques that they look to in order to elevate themselves. Something that you can do if you want to continue on is practicing and learning. There is a vulnerable driver that was released. The GitHub URL is right there. One of the really nice things about this driver is that when you're playing around with it, is that it does have the different vulnerability classes broken out, so you can sort of play around with the different ones. So I did want to close out with some things on Windows 10, because everybody's talking about Windows 10. There's some great talks this week. It's like, good. So the SMap ROP gadget that I did mention, it's in the exact same location. So from what I can tell, the technique in order to be able to bypass SMap by executing this gadget, it still is applicable. It's in the same function. Once again, you can't resolve that function, but it does still exist. One thing that I found was very interesting is that starting in Windows 10, the Win32K sys module is actually now broken out into 3 different parts. not sure why Microsoft did that, probably because it was growing very large, but a lot of the Windows vulnerabilities are in the Win32k.sys driver, so it would be very interesting to see how, if that affects exploits moving forward. So I doubt I have any time for questions because I ran incredibly late, but there's a ton of fantastic research out there on this. I have 2 full pages on some really great white papers that really taught me everything I know about Windows kernel exploitation. So I want to kind of share back my experiences with everybody and the tips and tricks that I found that increase reliability for exploits, because a local exploit specifically is no good if it's not reliable. So that was the first page. That was the second page. Some people were looking at it. Okay, and thank you everyone for waiting to get this presentation started, for spending your afternoon with me. Thanks everyone.